Alright, so now it's time to talk about covalent bonding, which is different than ionic bonding. In ionic bonding, we saw a transfer of electrons from one atom to another. Covalent bonding, we're going to share electrons. Specifically, we're going to share those valence electrons, hence the term covalent bonding, the sharing of valence electrons. Let's look at our first example here with one of our simplest molecules, the hydrogen molecule, one of our diatomic elements, Hofbrinkel. So when two hydrogen atoms get close enough together, the electron clouds merge and we get a single covalent bond. You can see here that this area is denoted as the molecular orbital, which we'll define here in a second. But when these two atoms are coming together, we have to overcome the fact that there is a repulsion between the two nuclei of the atoms. So when this nucleus gets closer to this nucleus, those two like charges don't want to be that close together. But that nucleus is attracted to the electron of the other atom. And so we're able to compromise, if you will, and end up creating this covalent bond. Why is this happening? Well, we are doing this, of course, because of stability. Two hydrogen atoms together are much more stable than either atom by themselves. Again, our atoms are on a quest for nobility. They want to be stable like the noble guests. And so now these hydrogen atoms merge together. They each think they have two valence electrons, which is just like a helium atom. Now here's an awesome little animated GIF of this happening that I don't want you to miss out on. So here we see two atoms, and then they link together and form a covalent bond. And when that happens, you can see a fantastic display of, bam, energy being released. Why is this energy being released? Because now together these two atoms are much more stable than they were as separate entities. And so here's another look at the covalent bond. When two atoms come together and share the electrons, that's what a covalent bond is. So what is this sharing of electrons known as? A covalent bond. And that space that these electrons occupy, right here, that is our molecular orbital. Just like we talked about orbitals being where the electrons are most likely to be found in an atom, well, when those orbitals merge together, when those electron clouds come together, then that's where the electrons are most likely to be found between the atoms in that molecular orbital. Courtesy of our good friend technology, we can indeed see covalent bonds, and I'll show you a picture of that here. This comes from a Discover magazine article, but here we see an image through an atomic force microscope of a nanographene molecule, and these green lines are actually showing the covalent bonds in between, which is kind of cool. I know it doesn't look like a lot to you here, but that, again, an amazing feat of technology that we can actually zoom in and see covalent bonds, molecular bonds. So how exactly do we know that a molecule is more stable? And this comes from our good friend potential energy. When there's less potential energy, that means it is a more stable situation. So here we see two hydrogen atoms separately with a potential energy of what we'll call 0. And as they move closer together, it looks like they're becoming more stable until all of a sudden down here we have the most stable position. The potential energy has drastically dropped, and that's like the ideal distance for the nuclei to be. Now if we try and squeeze those atoms together, the energy spikes back up. So again, we need to make sure that the nuclei don't get too close together. Here's a little visual of that happening, the hydrogen bond formation. So again, as the two atoms are here, it has a certain amount of energy. As they get closer together, boom, that's the most stable situation. And again, if you try and squeeze them too close, then we're going to see an energy spike, and we don't want that to happen either. So the perfect distance is this 75 picometers. In the video there was an A there, 74A, that's angstroms. It's just another metric measurement. But the bond length, the distance between the two nuclei of those hydrogen atoms, is 75 picometers. And this is an average distance, as this is what this little figure is showing. A bond is not a rigid structure. It is a flexible, moving structure, and so that 75 picometers is an average distance. The shorter the bond, the stronger it tends to be, and so it would take more energy to break that bond, which we call the bond energy. Here are some bond energies and the bond lengths for some single bonds. There are also double and triple bonds, which we'll talk about, but typically, the shorter the bond, the more energy is involved. So when bonds are broken and reformed, we can actually use these bond energies to calculate whether or not a reaction is going to be exothermic or endothermic. If the end products, if the bonds are more stable, then it's going to release that energy, which we'll feel as heat. If the resulting product is less stable, it's going to take more energy to get those bonds to form, so it's going to absorb it from around, and that it would be an endothermic situation. Now, nitrogen is held together at Hofbrinkel with a triple bond. And so that is actually a pretty strong bond and pretty short bond. And so you see the bond energy here for nitrogen at 946. And that is, excuse me, kilojoules per mole. And you can see that's much higher than any of these single bonds, which is why nitrogen and nitrogen-based compounds tend to be in a lot of different explosive materials, such as trinitrotoluene, dynamite. A lot of energy comes from the breaking of the nitrogen bonds. Just wanted to point that out to you as a little real-world practical application of those bond energies. So what we're going to look at now is how electronegativities can help us with bonding. If we remember, electronegativity was what we defined as how bad an atom wants an electron. And we said that fluorine happened to be the most electronegative element on the periodic table. Well, here is a list of electronegativities, and we can see right here that fluorine has a value of 4.0. This is the Linus Pauling electronegativity values. Fluorine is in fact the most electronegative, and most of the nonmetals have a pretty high electronegativity, especially compared to the metals. You can see way over here, francium, our least electronegative element, is down at 0.7. And so our nonmetals tend to have a higher electronegativity. They want to gain electrons to become stable, whereas the metals want to lose their electrons to become stable. And because of this, we will be able to tell if a bond between two elements will be ionic or covalent. Now, if it's covalent, we've got actually two types of covalent bonds. First up, we have a nonpolar covalent bond. This is the bonding in which the electrons are completely shared equally, like all the diatomic molecules, the twinsies of the periodic table. When two elements are very similar in nature, they'll have very similar electronegativities. And so they will want the electron equally, and we'll end up with this nonpolar bond. The word polar, you think of like polar bears, which comes from the North Pole. The Earth has a North Pole, South Pole. Batteries have poles, positive and negative. So nonpolar means none of that. We've got a total equal sharing situation. If we do have a polar bond, that's because the shared electrons that are in the molecular orbital are going to be pulled towards the more electronegative element. That element is going to want the valence electrons more. So we are not shared equally. Now, in this polar bond situation, we end up seeing the existence of what is called a dipole. Not a dipole, a dipole. This is found only in a polar bond. And we can visually draw this with what's called a dipole moment. And that's simply an arrow above the bond that is going to point towards the more electronegative element. So the bond between hydrogen and chlorine is a polar bond. Chlorine tends to be much more electronegative. How did I know that? Besides just being a genius, I know. But that's because of our electronegativity chart. Up here earlier we saw chlorine is 3.2, hydrogen is 2.2, and so chlorine is the more electronegative element. And so we have a partially positive end of the dipole and a partially negative end, and we'll see a better picture of that in a moment. But to draw a dipole moment, I just draw an arrow above the bond pointing towards the more electronegative element. So now we're going to use these electronegativities in an effort to figure out exactly what type of bond is going to form between the elements. So you can amaze your family and friends by asking them to give you two elements, and you can predict exactly what kind of bond is going to exist between them. So let's check that out. So here's a nice little diagram and chart. If two elements have a big electronegativity difference, like a metal and a nonmetal, we're going to end up with an ionic bond, because the one element is going to want the electron so much more, it's going to take it. And so when it takes it, it's going to become a negative ion. It's going to take it from something that's going to become a positive ion, and so we have the ionic bond. When elements are extremely similar, like our diatomics, they're going to totally share equally, and you can see an even electron distribution there. And that would be our nonpolar bond. In between that is the polar bond. And this is where we see a partially positive and partially negative situation. And here, this would be the more electronegative element that is pulling the electron towards it more. So we have the uneven electron distribution. So we see here that the larger the difference between the electronegativities, the stronger the bond. The ionic bond is much stronger than a nonpolar covalent and polar covalent bond. And then again, these little squigglies, those are the lowercase letter delta in the Greek alphabet, and stands for partially. So in our polar covalent bond, we have a partially positive and partially negative side. So let's see how we can predict what type of bond. So again, here we have our electronegativities and that little chart that tells us what type of bond we will have. So let's say between beryllium and fluorine. So beryllium has an electronegativity of 1.6. I blew that up for you here. Fluorine, 4.0. The difference, just subtract, and always do the big minus the small so we get a positive number. 4.0 minus 1.6, the difference is 2.4, and that would show up right here in the ionic portion. So we know we have an ionic bond. What about between nitrogen and oxygen? Again, subtract, find the difference. I just blew those up from the chart, and the difference is 0.4. And so 0.4 is over here in the nonpolar region. And so that is the type of bond. A nonpolar covalent bond will exist between those two elements. Another one here, lithium and hydrogen. The difference of that would be 1.2, and it's up here at the top though, but 1.2 falls in the polar covalent region. And so that is the type of bond that will happen between lithium and hydrogen. These are just a little easier to read if you want, but these are the rest of the samples. Take a moment and see if you can figure out those bonds. You can pause the video, and now I'll just give you the answers. But chlorine and chlorine, it's a diatomic molecule. Anytime you have the same element, the difference is going to be 0. That's our most nonpolar example. Germanium and sulfur with a difference of 0.6 is just slightly in that polar covalent region. And then potassium and fluorine, a very large difference of 3.2, definitely ionic. Because you memorized elements and polyatomic ions, don't worry, you will not have to memorize the electronegativity charts. I will give you that, as well as this convenient little chart when it comes to a test or quiz, so you should be able to easily identify what type of bond will exist between different elements. Don't forget, you can amaze your family and friends with the same task, as you can just look that up and say, I believe it'll be this type of bond. Alright, thank you very much. See you next time.